To motivate what this means in the real world, I want to talk a little bit about human auditory range. The human auditory range runs from about 16 hertz to about 16,000 hertz. And what that means in terms of what you hear can be demonstrated by looking at the keyboard of a regular piano. You can see that spans much of this full spectrum. We can also see that male speech and female speech are also well within that spectrum. What is interesting is that this is broken into three areas typically when people look at acoustics. There's low frequency, which runs up to about 300, sometimes people would say as high as 500 hertz, and that's typically solved with FEA, with finite elements. And then there's high frequency, which is 1,000 hertz and above. Interestingly, there has been what's known as the mid-frequency, which is also known as a gap, because this is not adequately solved with either technology today. If we define the mid-frequency as 300 hertz to about 1,000 hertz, this has historically been a somewhat intractable problem to solve. FEA was not capable to span that high due to what you already saw, 16-day run times to span that gap. In statistical energy analysis, the high frequency solution was fundamentally not able to go lower for reasons we won't get into. So this 300 to 1,000 hertz gap is quite problematic when we consider sitting in a car and things like listening to music and talking to each other. And we can see that by this chart. If we look at voices, a low male voice fits well in the low range. However, a high male voice starts splitting into the low to mid frequency range, and a medium female's voice is likewise low to mid frequency. A high female voice, a soprano, is smack in the middle of mid frequency range. The consequence of this gap, shown in gray here, is that we're not able to capture the effect of vehicle noise in the very region which is probably most interesting to us, human conversational tones. And this has been a quandary for automotive NV engineers. To demonstrate the implications of this, I'm going to ask for help from a few of my colleagues. I'll first have Vladimir Belsky talk.
I'm a bass or low baritone, so I really don't need much more than the low frequency range. We will now filter out all of the frequencies above 300 Hz as I speak. You can now hear a difference in my speech, but my voice is still clear. For my vocal range, we can predict how the car's acoustics will affect me. However, most people don't have voices as low as mine.
I, on the other hand, am a tenor, and my voice ventures into the mid-frequency range. We will now filter out everything above 300 Hz, which is a typical technology employed today using finite elements.
When everything above 300 Hz is filtered out, my voice is noticeably duller. Today's deployed technologies are not able to effectively predict how car noise would interface with this upper portion of my voice. So that which you can hear that we've lost above 300 Hz is essentially what is lost numerically with today's simulation solutions.
On the other hand, we now filter out only everything above 1,000 Hz. You can hear that my voice is much clearer and richer in this range, the range that Abacus is now able to predict within the car. Finally, we will listen to Maria Williams and the impact of this technology on understanding vehicle noise on a woman's voice.
I am a soprano, and my voice is almost entirely in the mid-frequency range. We will now filter me above 300 Hz.
You can hear how different my voice is. The current state of the art cannot capture anything that impacts the richness of my voice. It's as if it can only capture what you're hearing right now. With these limits, there's almost no ability to understand how my voice is affected by vehicle noise.
If we now filter only above 1,000 Hz, my voice is still not as rich as before, but it is much closer to my full voice. This additional richness is what Abacus can capture and understand in the vehicle that other codes cannot.
So the real consequence of this technology is that Abacus is now able to effectively solve both low and mid-frequency noise and vibration problems in one fell swoop. This capability presents to our customers a new frontier in noise and vibration analytical prediction previously unavailable to them. Automotive companies can now simulate the impact of noise across the full human vocal and auditory ranges using our technology alongside the already established higher frequency technologies. This introduces a new reality to all of our customers and all of our potential customers. We have not solved noise up to 1,000 hertz. However, we have now given automotive engineers the tools necessary to solve these problems, tools which were previously unavailable to them.